When we learned how to integrate a function of two variables over a region in the plane, we first learned how to integrate over a rectangle, and then we learned how to integrate over more general regions, specifically a type 1 region and a type 2 region. Now we're in an analogous situation with integrating a function of three variables over a solid region in space. We have learned so far, we've learned how to integrate a function of three variables over a rectangular box using Fubini's theorem for triple integrals. And now we're ready to learn how to integrate a function of three variables over a more general type of solid region. Specifically, we're going to learn how to integrate a function of three variables over what's called a type 1 solid, and also over what's called a type 2 solid, and also over what's called a type 3 solid. Here's a picture of a type 1 solid. This solid region E, shown in blue, is a type 1 solid. This region D is in the xy plane is the projection of E onto the xy plane. D consists of all points in the xy plane that are below E. If the sun were shining down directly from overhead, then D would be the shadow of E. D would be the shadow of the solid object E. And if it were raining straight down, then D is the region that would stay dry because it's underneath E. The lower surface of E, the lower surface, is the graph of this function u1. And the upper surface of E is the graph of this function u2. This type 1 solid E can be described as follows. E consists of all points x, y, z such that the point x comma y belongs to D, and also z is in between u1 of xy and u2 of xy. Here it is written on paper. E is the set of all points x, y, z such that the point x comma y belongs to D, and z is in between u1 of xy and u2 of xy. This is the definition of a type 1 solid. Now, how do we integrate a function of three variables over a type 1 solid? Here's a fact that will tell us how to integrate over a type 1 solid. This is a fact. The integral over E of a function f of x, y, z dv is equal to the integral over D of the integral from u1 of xy to u2 of xy, f of x, y, z dz dA. This is our fact. This will tell us how to integrate over a type 1 solid. In this inner integral here, we're integrating with respect to z. Z is going from u1 of xy, which is the starting value of z, up to u2 of xy, which is the final stopping value of z. We're integrating with respect to z. In this inner integral, we're thinking of x and y as being held fixed. This expression here can be viewed as being a function of x and y. I give you x and y, and you perform this integral with respect to z, holding x and y fixed, and the result is a number. So this expression, we can view it as a function of x and y. We could call this expression w of x, y. And in this outer integral, what's happening in this outer integral is we're integrating over a region D in the xy plane. And we're integrating this function w, which is a function of two variables. W is a function of x and y. It's a function of two variables, and we're integrating this function of two variables over a region D in the plane. But integrating a function of two variables over a region in the plane is something that we already know how to do. In particular, suppose that D happens to be a type 1 region in the plane. In other words, suppose that D can be described as follows. Suppose that D can be described as the set of all points x comma y such that x is in between A and B and y is in between g1 of x and g2 of x. This is how a type 1 region can be described. If D is a type 1 region like this, then the integral over D of w of x, y, dA is equal to the integral from A to B of the integral from g1 of x to g2 of x of w of x, y, dy, dx. This is the formula that we learned earlier for how to integrate a function of two variables over a region D of type 1 in the plane. This is the iterated integral that we get. So now, let's plug in the expression that we wrote down for W. This is equal to the integral from A to B of the integral from g1 of x to g2 of x. And now I'm going to replace w of xy with the expression that we wrote down earlier, with this expression here. That's our expression for w of xy. W of xy is equal to this integral where we're integrating with respect to z. It's this expression in brackets here. So I'm just going to write that down. What we have here is the integral from u1 of xy to u2 of xy of f of xyz dz, and then here we have a dy, so I put a dy here, and here we have a dx, so I have a dx here. So here we have arrived at our formula for integrating a function f of three variables over a type 1 solid E. The integral over E of f of x, y, z dv is equal to this iterated integral. This formula, let me put a box around this formula. This is the formula that we will use to evaluate integrals over a type 1 solid. Now, that formula was derived under the assumption that D was a type 1 region in the plane. What if instead D was a type 2 region in the plane? If D is a type 2 region, then that means D can be described like this. D is the set of all points x, y, such that y is in between C and D, and x is in between h1 of y and h2 of y. In this case, when D is a type 2 region, the integral over D of w of x, y dA is equal to, and now with a type 2 region, the outer integral goes from C to D, and the inner integral goes from h1 of y to h2 of y, and we're integrating w of x, y. The inner integral is now with respect to x, and the outer integral is with respect to y. This is how we integrate over a type 2 region in the plane. So what this means is that in this case, the integral over our solid region E of the function f of x, y, z, this integral turns out to be equal to the integral from c to d of the integral from h1 of y to h2 of y. And now I'm going to replace w with the expression that we have for w. Remember, this is the expression that we have for w. So w gets replaced with the integral from u1 of xy to u2 of xy, f of x, y, z, dz, and here we have dx, so I'm going to write dx, and here we have dy, so I'm going to write dy. So this is a different formula that we get in the case where D is a type 2 region. So we have to be careful about those two different cases. If we're integrating over a solid region E, which is a type 1 solid, then there's two separate cases. Either this region D in the plane, the projection of E onto the plane, this projection could be a type 1 region, in which case we get one formula, or it could be a type 2 region, in which case we get a different formula. So now we know how to integrate a function of 3 variables over a type 1 solid region. Now let's look at how do we integrate a function of 3 variables over a type 2 solid region. Suppose we want to integrate a function of 3 variables over a solid region E, which is a type 2 solid, meaning it can be described like this. E is the set of all points x, y, z, such that the point y comma z belongs to D, and here D is the projection of E onto the YZ plane, and so the point YZ belongs to D, and X is in between U1 of YZ and U2 of YZ. This is how a type 2 solid can be described. And here's a fact that will tell us how to integrate a function of 3 variables over a type 2 solid region. The integral over E of a function f of x, y, z is equal to the integral over D of the integral from u1 of yz to u2 of yz, f of x, y, z. This inner integral is with respect to x. And the outer integral is, in the outer integral, we're integrating over the region D in the YZ plane. So I'm going to write dA. In this case, this expression here can be viewed as being a function of y and z. We could call this w of y comma z. And this function of 2 variables is being integrated over this region D, which is a region in the YZ plane. And once again, we have 2 separate cases to consider. Case 1 is where D is a type 1 region in the YZ plane, and case 2 is where D is a type 2 region in the YZ plane. Let's look at the case where D is a type 1 region in the YZ plane. That means D can be described like this. D, it consists of all points y comma z, such that y is in between C and D, and z is in between G1 of y and G2 of y. In this case, the integral over D of w of yz dA is equal to the integral from C to D of the integral from G1 of y to G2 of y of w of y comma z. The inner integral is with respect to z. The outer integral is with respect to y. So this inner integral is with respect to z. The outer integral is with respect to y. Now, let's return to let's go back and look again at our expression for w of yz. This is our expression. If we plug in this expression for w of yz, then what we get is the integral from c to d of the integral from g1 of y to g2 of y. And now w of yz becomes, that's equal to the integral from u1 of y comma z to u2 of y comma z of f of x, y, z dx. And then here we have a dz, so I put a dz here. And here we have a dy, so I put a dy here. And this is our formula for the integral over e of f of x, y, z dv. This is our formula. Here we have E as a type 2 solid region, and its projection onto the YZ plane is a type 1 solid region. This is the formula that we end up with. And all the other cases are going to work out in a similar way. Suppose the projection of E onto the YZ plane is a type 2 region in the YZ plane instead of a type 1 region. Well, a similar thought process would lead to a similar formula. Or suppose that E, our solid region, suppose it's a type 3 solid region. We could go through the same thought process and we could come up with formulas in that case also, similar formulas. So here's a summary of how to integrate over each of our 3 special types of solid regions. If the region E that we're integrating over is a type 1 solid region, then we should look at the projection of E onto the XY plane. If E is a type 2 solid region, look at the projection of E on the YZ plane. And if E is a type 3 solid region, look at the projection of E onto the XZ plane. And then in each case, draw your picture. It helps to draw a picture, 2 pictures, a picture of E and a picture of D, the projection of E. And then you can go through a similar thought process to what we just went through, and you can write down a formula that expresses your integral over the solid region E as an iterated integral. Let's do an example problem. In this problem, we want to integrate this function over the solid tetrahedron E shown in this picture. You can see that this tetrahedron, it's bounded on this side by the XZ plane. It's bounded here on this side by the YZ plane. It's bounded below by the XY plane. And it's bounded also by this surface. And this surface is, the equation for the surface is z equals 1 minus x minus y. So you can visualize this solid tetrahedron here. And we want to integrate this function over that solid region, that solid tetrahedron. Let's visualize the projection of this solid region onto the XY plane. That projection is just the little triangle that we see here. Let's call that, this little triangle, let's call that D. D is the projection of our solid tetrahedron E onto the XY plane. And let's draw a separate picture of D. So here is the y, here's going to be my y-axis, and here is my x-axis, and here's, so x, y, and here's the point 1, 0, and here is the point 0, 1, and I'll just draw that line. This triangle here is our region D, the projection of our solid E onto the XY plane. And now that we have visualized D, we can recognize that E is a type 1 solid region. We can describe E as follows. E is the set of all points x, y, z, such that x comma y belongs to D. This x comma y belongs to D, and z is in between 0 and 1 minus x minus y. Our solid tetrahedron can be described like this: 1 minus x minus y. And this shows that E is a type 1 solid region. And moreover, the projection of E onto the xy plane, this region D, this is a type 1 region in the xy plane. So now we're ready to start setting up our integral. So because E is a type 1 solid region, we're going to start by writing this down. The integral over E of z dv is equal to the integral over d of the integral from 0 to 1 minus x minus y, and then z. And then here I'm going to write dz, and then the outer integral. In the outer integral, we're integrating over this region D here. Okay, now because this region D is a type 1 region, we know how to integrate over the region D. So this integral over the region D, we can write that as the integral from 0 to 1, and then we have the integral from 0 to 1 minus y. So is this clear? Why is the upper limit 1 minus y? If we look at this picture, the equation for this line is y equals 1 minus x. That's the equation for this line. So in this picture, for any given value of x in between 0 and 1, y goes from 0 up to 1 minus x. So when we integrate over this region D, you can imagine x goes from 0 to 1. X goes from 0 to 1, and for any specific value of x, y goes from 0 up to 1 minus x. So here, I should have a 1 minus x here. That should be 1 minus x. X goes from 0 to 1, y goes from 0 to 1 minus x. And then on the inside, I still have the integral from 0 to 1 minus x minus y, and the function I'm integrating is z. This inner integral is with respect to z, and then I have dy and then dx. So this is our iterated integral, and this is what we need to evaluate. And that's the hardest part, is setting up this iterated integral. Because to set up this iterated integral, you have to take a look at the solid region that we're integrating over. You have to recognize it's a type 1 solid region. You have to visualize its projection onto the xy plane. And then you have to recognize that this projection region, this region D, is a type 1 region in the plane. And then you think it through, and you come up with this iterated integral. And that's the hard part. And now we just have to evaluate this iterated integral. So let's first evaluate this innermost integral. We need to find an antiderivative of z, of the function z, with respect to z. Of course, that's just z squared over 2. And we evaluate this antiderivative from 0 to 1 minus x minus y. And when we plug in 1 minus x minus y for z, we get 1 minus x minus y squared over 2. When we plug in 0 for z, we just get 0. So the inner integral evaluates to 1 minus x minus y squared over 2. Now, let's do the next innermost integral, this integral with respect to y. We have to do integral from 0 to 1 minus x, and we're integrating this thing. So we're integrating 1 minus x minus y squared over 2 dy. We need to find an antiderivative of this with respect to y. And here's an antiderivative, negative 1 minus x minus y cubed over 6. We could check that this antiderivative is correct just by taking the derivative of this thing with respect to y. And if we do that, we use the chain rule and we see that we get the correct answer. So this is our antiderivative. Now we have to take this antiderivative and evaluate it from 0 to 1 minus x. And what happens when we plug in 1 minus x for y? Well, then we have 1 minus x minus 1 minus x. That gives us 0. Okay, what happens when we plug in 0 for y? Then we get just 1 minus x cubed over 6. So this evaluates to 1 minus x cubed over 6. Good. So we did the two innermost integrals and we ended up with this. And now we're ready to evaluate the final outermost integral, which is with respect to x. So we need an antiderivative of this function with respect to x. And here's an antiderivative, negative 1 minus x to the 4th over 24. You can check this is correct just by taking the derivative and checking that you get this. Now let's take our antiderivative and evaluate it from 0 to 1. When we plug in 1 for x, we have 1 minus 1, which is just 0. When we plug in 0 for x, we have 1 over 24. So our final answer is 1 over 24. Here's another way to think about setting up your triple integral. And this way of thinking about it might get you to the answer a little more directly, even though it's equivalent to what we've been doing. Suppose we want to integrate a function of 3 variables over a solid region E, and suppose that E can be described like this. And notice the pattern here. X is in between A and B, which are constants. And Y is in between G1 of X and G2 of X. And then Z is in between U1 of XY and U2 of XY. So the first variable in our list is bounded on either side by constants. The second variable is bounded by expressions that depend only on the first variable. And then the final variable in our list is bounded on either side by expressions that involve only the previous variables, x and y. So if you can express E like this, then the integral over E of f of x, y, z dv is equal to the integral from a to b of the integral from g1 of x to g2 of x of the integral from u1 of xy to u2 of xy f of x, y, z dz dy dx. The innermost integral is with respect to z, and the limits are z goes from u1 of xy to u2 of xy. The second innermost integral is with respect to y. Y goes from g1 of x to g2 of x, so that's why we have g1 of x to g2 of x here. The outermost integral is with respect to x, and x goes from a to b. So once you have described your region, once you have described the solid region that you're integrating over in this form, then you can just write down your integral. And if you think about it, this is equivalent to what we've been saying, but it's maybe a slightly more direct way to get to the final answer. Here's another example of this slightly different way of thinking about setting up your triple integral. Suppose the solid region we're integrating over, the solid region E, can be written like this. Here, y is in between c and d, which are constants. X is in between h1 of y and h2 of y. This expression here depends only on the previous variable. This expression here depends only on the previous variable. And then finally, z is in between u1 of xy and u2 of xy. So you see the pattern. The first variable in the first variable is bounded by, it's between these constant values. It's bounded by these constant values. The second variable is bounded by expressions that depend only on the previous variable. And then the final variable is bounded by expressions that depend on the previous two variables. That's the pattern. Once you've expressed e this way, then we can just immediately write down the integral over e of f of x, y, z dv is equal to, and the outermost integral is going to be from c to d, and it's going to be with respect to y. The next integral is going to be from h1 of y to h2 of y, and it's with respect to x. And then the innermost integral is from u1 of xy to u2 of xy, and we're integrating f of x, y, z, and the innermost integral is with respect to z. So once you've described your solid region according to this pattern, then you can just write down your iterated integral. You can write down your triple integral quickly. This is the hard part, figuring out how to describe e according to this pattern. So let's look at another example. In this example, we want to integrate this function over the region E, where this solid region E, it lies under this plane, and it lies above the region in the xy plane that's bounded by the curves y equals square root of x, and y equals 0, and x equals 1. Let's draw this region in the plane, let's draw this region in the xy plane. And here's the xy plane. Here's the curve y equals square root of x. Here is x equals 1. So the line x equals 1 is this line. Y equals 0, that's just the x-axis. So the region that we're looking at in the xy plane is this region. And E is the solid region that lies under this plane and above this region in the xy plane. So E can be described like this. E consists of all points x, y, z, such that x is between 0 and 1, y is in between 0 and the square root of x, and finally, z is in between 0 and 1 plus x plus y. This is our description of E. And we see the pattern here. The way we have described this, you see the pattern the way we've described this. X, the bounds on x are constant. The bounds on y depend only on x. These bounds on y depend only on the previous variable. The bounds on z depend only on the previous two variables, x and y. Once we've described E like this, we're ready to set up our integral. Now that we have this description of E, we're ready to write down our iterated integral. The integral over E of the function 6xy is equal to the integral from 0 to 1. The outer integral goes from 0 to 1, and the outer integral is with respect to x. And the next innermost integral goes from 0 to square root of x, and this integral is with respect to y. And then the innermost integral goes from 0 to 1 plus x plus y, and the function we're integrating is 6xy, and the innermost integral is with respect to z. So now we have set up our integral, and at this point, it's sort of a routine calculation to actually evaluate the integral. The hard part is over. Now we just have to go through the process of evaluating these integrals one by one. Setting up the integral is the hard part. Now let's look at one final example. We want to integrate this function over the solid region E, which is described like this. E is the solid region bounded by this paraboloid and the plane x equals 4. So if we visualize this paraboloid, this is a paraboloid that opens along the positive x-axis. It's a paraboloid that opens along the positive x-axis. And then this plane x equals 4, that chops the paraboloid. So we're visualizing the solid region E that you get by taking the inside of this paraboloid and chopping vertically at x equals 4. If you picture the projection of this solid region E onto the YZ plane, it's a disk of radius 1. It's a disk of radius 1. This solid region E can be described like this. E consists of all points x, y, z, such that, and here I'm going to say y is in between -1 and 1. Z is in between the square root of 1 minus y squared and minus the square root of 1 minus y squared, like this. And then finally, what about x? X is less than or equal to 4, and x is greater than or equal to 4y squared plus 4z squared. This is a description of our solid region E, and notice the pattern that we're following. The bounds on y, the bounds on our first variable listed here, are constants. And then the limits, the bounds on z, depend only on the previous variable y. And then the bounds on x depend only on the previous two variables. Once we've described E like this, we're ready to write down our integral. By the way, can you see that these first two equations describe a disk of radius 1 in the YZ plane? Describing E like this was the hard part, and now, once we've done this, it's easy to write down the integral. So the integral over E of x dv is equal to the integral from -1 to 1. The outer integral is with respect to y. And the next integral is from square root of 1 minus square root of 1 minus y squared up to square root of 1 minus y squared. And this integral is with respect to z. And the innermost integral is from 4y squared plus 4z squared up to 4. The function we're integrating is just x. This innermost integral is with respect to x. So here, now we have set up our integral. And at this point, that was the hard part. In principle, it's straightforward to just evaluate these integrals.